So this is the component of the remote sensing mission. The electromagnetic energy provides the information necessary for remote sensing. This energy is either emitted by subject, in example the sun, or reflect off the subject. As example, the ship at the sea. For example, if a spacecraft needs to detect a plane in flight, the electromagnetic radiation originated at the sun travel through the space and through atmosphere. It then reflects off the aircraft, carrying information back through the atmosphere for the sensor on the spacecraft to detect. Computer on the spacecraft process the detected radiation, forming an image of the aircraft, which is relayed to the user on the ground. And this is the electromagnetic spectrum. Electromagnetic waves transmit in form of radiation. We can describe it as either particle or wave motion. Electromagnetic waves spread out from the source, traveling at speed of light, 300,000 km per second. Because payloads can use different parts of electromagnetic spectrum, we need to understand how we describe this different type of radiation. The distance from crest to crest is called wavelength or lambda. The number of waves that go by in 1 second is the frequency. So if 10 waves or cycle go by per second, the frequency is 10 cycle or hertz. The time it takes for just one wave to go by is 1 per frequency. That is, if the frequency is 10 hertz. And energy in electromagnetic radiation relates to the number of waves that hit an object during a given time. Thus, 10 waves hitting in 1 second deliver twice energy of 5 waves. This energy relationship can be expressed as Q equal to hash F. This equation implies more energy is available at higher frequency, so higher frequency waves have more energy than lower frequency wave. For example, radio frequency have much less energy than X-ray. That's why we can walk through radio wave all day long without worry, but must take extra precaution around medical X-ray equipment. So whenever electromagnetic radiation hits an object, one of three things can happen. The object transmit, reflect, or absorb the energy. From the principle of energy conservation, the sum of the transmitted, reflected, and absorbed energy must be equal to the total energy that initially hits the object. The amount of the energy depends on the wavelength of the incident energy and the property of the material. We will later study the importance of transmission, reflection, and absorption to remote sensing mission. So, the atmosphere is selectively transparent to the different wavelength of radiation. On the cloudless day, we can see light from the sun, feels its heat, and get sunburn from UV light. On cloud day, some light and heat are blocked, but some UV radiation still get through. For remote sensing, we want to collect the electromagnetic radiation reflected by or emitted from object on Earth's surface, while our spacecraft is above the atmosphere in space. The electromagnetic wavelength typically utilized for remote sensing of the Earth's surface or atmosphere range from the ultraviolet to microwave region or spectrum. Useful information can be extracted from remote sensing data because different types of objects on Earth's surface tend to have different electromagnetic reflectance or emittance properties. That is to say, they have different spectral characteristics. This figure shows the strength of reflection and radiation of electromagnetic wave from plants, earth, and water in each wavelength. So this figure shows the percentage of each wavelength of electromagnetic radiation that passes through the atmosphere. You may notice that some wavelengths such as visible light are completely transmitted while others are almost completely blocked. We see that our spacecraft instruments have access to Earth from space through various windows of transmission. Atmospheric windows are the wavelengths that are 80% to 100% transmitted through the atmosphere. The most notable atmospheric windows are the visible, infrared, and radio wavelength. Using the visible and infrared window, spacecraft instruments can peer through the atmosphere to sense property of objects on Earth from space. We use radio frequency window to pass television and radio signal from studio on the ground through satellite to our living room. And the absorbed energy causes an object to heat up. However, some objects are already hot and emitted their own heat. It is easy to imagine that the sun at 6,000 Kelvin emits energy we call sunshine. Objects emit electromagnetic radiation at different wavelengths depending on their material property and temperature. To determine the best frequency to use to see a particular subject, we need to know the subject temperature and then design a sensor tuned to frequency of maximum output for that temperature. For example, if we need to detect the hot plum from rocket exhaust, we need to know its temperature and the design a sensor tuned to the frequency of maximum output for that temperature. We can also determine the total power output of a radiation by using Stephen-Boltzmann equation, developed by Joseph Stephen and derived by Ludwig Boltzmann. This equation estimates the total amount of energy available over all wavelengths for a specific temperature. So this panchromatic image and panchromatic images are obtained by recording radiation in a single wide bandwidth within the visible part of spectrum, in example between 0.4 and 0.7 micrometer. Because the data are stored in one single channel, only black and white image can be produced. The spectral information contained in a panchromatic image is rather limited, but such images generally have a higher spatial resolution. This is another example of panchromatic image taken above Washington, D.C. The multispectral data are acquired by simultaneously recording 3 to 8 different spectral bands that may or may not be contiguous. To visualize this information as a color image, primary colors red, green, blue are paired with spectral band. The relative brightness, which depend on its digital value of each pixel in each primary color band, determine the resulting color in the combined band. The amount of information is enormous and require considerable more computing power than in the case of multispectral image. The application of imaging spectroscopy are manifold. The most important are geology to identification of mineral, precision farming, forestry, and management of aquatic environment. As the hyperspectral remote sensing combine imaging and spectroscopy in a single system, which often include large datasets and require new processing methods. Hyperspectral datasets are generally composed of about 100 to 200 spectral bands of relatively narrow bandwidth, 5 to 10 nanometer, whereas multispectral datasets are usually composed of about 5 to 10 bands of relatively large bandwidth, 70 to 400 nanometer. Hyperspectral imagery is typically collected and represented as a data cube with spatial information collected in the XY plane and spectral information represented in the Z direction. There are many applications which can take advantage of hyperspectral remote sensing, such as atmosphere to monitor water vapor, cloud properties, and aerosol. In ecology, to detect chlorophyll, leaf water, cellulose, pigment, and lignin. And in geology, to locate mineral and determine the soil type. As for spatial resolution is the number of pixels per millimeter defined as a digital image resolution. In remote sensing, the image resolution are expressed by the size of the area covered by a pixel. Each pixel in an image corresponds to a patch on the Earth's surface. We thus talk about the ground resolution. This figure is to show the importance of the resolution for the picture quality started from the low resolution to the highest resolution.